Okay, this is our third video showing the solution to problem 3 from quiz 3. So here we're given a table of Laplace transforms, right? These are all things that either in the homework or in class we had worked out. And we wanted to use this table to compute other Laplace transforms. And so there's two things I didn't give you here, but which you should know from the homework. The first of them, right, that we could add here is that if I take the Laplace transform of a sum of functions, that this is equal to the sum of the Laplace transforms of the functions. And if we wanted to worry about the s here, we know if the L of f rather, required s to be greater than a, and the L of g required s to be greater than b, then the L of f plus g is going to require the s to be greater than both. Okay, so we would basically just pick whichever one's bigger, right? So s is greater than the max of a and b. Okay, so that's something you should know. And then another thing you would want to know is that if I multiplied f by some constant and take the Laplace transform, then instead I could pull the constant out, compute the Laplace transform of f, and then multiply by that constant. So in the language of linear algebra, this first one is called additivity. So the Laplace transform is additive. And the second one is called homogeneity. So the Laplace transform is homogeneous. And if you combine these together, you would say L is linear. Okay, that is essentially a linear transformation, much like the derivative and the integral are. Okay, so what that tells us, say for part A, is that we can rewrite part A as, well, I can pull the constant out and write L of t to the fourth and break it up at the minus sign, right? So it doesn't matter plus or minus. Break this up. Minus twice the Laplace transform of e to the 5t minus the Laplace transform of t cubed plus the Laplace transform sine of negative 7t. Okay, notice that I'm not pulling a negative 7 out because it's trapped inside the sine, right? And that's not one of the properties of the sine function. You can't pull a negative 7 out of the sine function. All right, so now I can use the table, though, and I get 3 times, so I need the Laplace of t to the fourth. So I go up here to the top one, and I say, okay, if it's t to the fourth, it'll be 4 factorial over s to the 5th power. Okay, then minus twice. Okay, now I need the Laplace of e to the 5t, so I use the second one. E to the at, well, my a is 5 here, so this would be 1 over s minus 5. Okay, then I have a minus, and now I need L of t cubed. Okay, back to the first one. N is now 3, so I'll get 3 factorial over s to the 4th power. Okay, and then finally I have plus. Okay, I need the Laplace of sine of negative 7t. So sine of at, okay, my a is negative 7. So I would have negative 7 over s squared plus 7 squared, right, or negative 7 squared, which is 49. All right, now I have also been given another instruction, which we have to read, right? We need to decide for which s the Laplace transform is defined. So if you look at your table, right, it'll tell you this Laplace transform is defined when s is positive, whereas the one for e to the at is only defined when s is greater than a. You remember these usually showed up because when we were trying to compute the improper integral that defined these things, we needed to make sure it converged. And so in almost all those cases, what we were dealing with, right, was multiplying our function by a decaying exponential. At least it decayed provided s was big enough. All right, well, let's see what's happening in each of these. So for the first one, we're just using the Laplace of t to the fourth, which came from this first entry in the table, which says s just has to be positive. Let's write that underneath it. Okay. The second one comes from e to the at, which requires s to be greater than the a, and in our case, our a was 5. So s had to be greater than 5 for this one to converge. This next one is back to the first entry in the list, so s had to be positive. And also for the sign, s had to be positive. Okay. So for all 4 of these to work, we need all of these to be true. Well, 3 of these are just repeated, s being positive, s being positive, s being positive, but the fourth one is that s has to be greater than 5. So our total condition, right, for all 4 of those to hold, we just need s to be greater than 5. All right, let's try the second one. Okay, so this is B. So here, we're asked to compute the Laplace transform of the hyperbolic sine of AT. However, we've been given a very helpful hint. The sine of AT, or hyperbolic sine of AT, can be rewritten in terms of exponentials. Well, let's try that. So the Laplace transform of the hyperbolic sine is equal to the Laplace transform of, well, let's see, there's a half, which I could pull out, e to the at minus e to the negative at. If I pull the half out, then what do I have? Well, I have a Laplace of a difference, so I could break that up. I could have the Laplace of e to the at minus the Laplace of e to the negative at. And now I can just go back up. Oh, just jumps off the screen a little bit. Right. The Laplace of e to the at is 1 over s minus a. So I get 1/2. Okay, well, that's just a direct just copying, right? 1 over s minus a minus, now the a is switched to a negative, so I get 1 over s plus a. All right, well, I should be able to put those together. So let's see. This will be s plus a minus s minus a over, well, let's see, s minus a times s plus a, that's s squared minus a squared. All right, now let's see, I have s minus s. Those will cancel. Notice I don't cross them out, though. But these s's will cancel, and then I have a minus negative a. That's a plus a is 2a, which I'll divide by 2, just to get a. So I get a over s squared minus a squared. Okay, an easy way to have gotten this problem wrong would be to use the definition of the Laplace transform. Not that you can't compute the Laplace transform that way. It would just mean that you didn't, what is that? RTI? Read the instructions, right? We want to use the table to compute it, not the definition. All right, so that's how we can do that one. Now, of course, there's still this other issue of what is the s. Well, the first, we basically had to compute 2 Laplace transforms to make this work. And the first one, the assumption is that s has to be greater than a. The second one is that s has to be greater than negative a. Okay, so a could be positive, a could be negative, so one of these is going to be positive, and so what we can do is just say, well, let's make s greater than the absolute value of a, and that'll handle both of them, right? If we draw this on a number line, okay, what you're probably thinking is that it looks like that. Okay, but it could be the opposite, right? If a is negative, then negative a would be the positive one. Okay, but in either case, whichever one is the bigger one, that'll be the absolute value of a. So we can just make sure, right? S just has to be bigger in either case. So putting the absolute value will make sure S goes into that region.